Hey guys, welcome back. This is day 7 of rotational dynamics, and yesterday we've talked about, we've completed the idea of moment of inertia, and we started the problems with torque equals to I alpha. I've even discussed a basic problem of a disk. When you apply some force on it, what is the angular acceleration of the disk, and we end up with this formula. So, which is clear by yesterday, and today I said I would discuss a lot of problems, right? Like problems like this, I will definitely discuss a lot of things. Let's start with a very basic problem. Okay, I'm starting with a very basic level problem, and slowly we get there. Let us start with a problem where there is a rod hinged by the middle, a rod hinged by the middle. Did I not put my phone on silent? No, I didn't. Yeah, rod of mass m. The length of the rod is also given L. Okay, it's state of balance. Let's just say there is no gravity, but even if there is gravity, someone applied a force F at the end, at the edge. What is the angular acceleration of the rod? Do a quick math and tell me the answer. Like, it's really easy. Someone applied a force F on the end of the rod. What is the angular acceleration that is created in the rod? Anybody? I'm waiting. Give me the answer. Okay, some answers are coming already. Ganesh already gave the answer. Good. But Ganesh, do you think your answer is right? I think you put the moment of inertia of the rod wrong. Check that once. Harshavardhan also sent some answer. Mazida, I think your answer is right. Mazida says some value. I think the answer is right. Ganesh and Harshavardhan, I think you messed up with the values. Sai Harshita also sent the right answer. Good. Right, guys, check this. The perpendicular distance, first of all, is L by 2. The rod is hinged in the middle. So the torque created, torque equals to I alpha. Torque created is nothing but F into L by 2. Now the rod is hinged in the middle. What is the moment of inertia of a rod which is hinged in the middle? It is ml square by 12 into alpha. Please check where you have gone wrong. Okay. L cancels out to 6. So alpha is nothing but 6f by ml. That is the angular acceleration of the rod. Okay, so this is how you need to solve these kind of problems. I'm going to give you one more problem. I want an immediate answer, completely similar problem. Okay, I'm not going really far away. Same mass, same length, a force 3f here, a force f here, which is at a distance L by 4. Okay, this is at a distance L by 2 only. A quick answer, guys. Come on, make it quick and give me the answer as quick as possible. What is that? I don't know. Okay, guys, you're way too slow. You're way too slow for my class. Did you all just wake up from a good sleep right now? Because I did. Nope, no answer yet. Come on, guys. All you have to do is look at two torques. One torque is in this direction, the other torque is in the opposite direction. So I'm going to write the torques 3f into L by 2. I'm going to consider that as a positive direction. And the other one, minus f into L by 4. 3f into L by 2 minus f into L by 4. That is the net torque, which is equals to I into alpha. Moment of inertia of the rod is ml square by 12. This comes as 4, 6 FL minus FL. So 5 by 4, 3, 5 FL into 3 by ML. So 15 F by ML, guys. The answer is 15 F by ml. Majida got the wrong answer. Dhanush sent the right answer this time, except he missed an L there. But anyway, the rest of the idea is right. So guys, you need to be really quick, like when you're doing problems like this. It's a basic problem only. Now I want to add something to this problem. Make the problem a little bit tough compared to the previous situation. The same rod, except I stick a net. This rod's mass is m, length is l. I stick a block, like let's just call it as a point mass. Let's simply call it as a point mass, okay? Let us simply call it as another point mass. The rod's mass is m, a point mass is also m, length is l. Aditya is asking, sir, can you once do the derivation of solid cylinder where the axis is passing? Aditya, we will do that later. Like you should have asked me before I started the class. Anyway, if you're still talking about moment of inertia, talk to me after the class. Look at the problem right here. The entire rod's mass is m, the length, entire rod's mass is m, and there is another particle mass which is added at the end of the rod. Now, doing this question, you need to be really careful. Okay, you need to be really careful. Let us look at all the forces. One of the mg is acting here, the other mg is acting here. Only one mg is capable of creating torque. This mg is not, because it is passing through the center. It won't create any torque. This mg will definitely create some torque. So the torque acting, the net torque acting on the body is nothing but system is nothing but mg into L by 2. We are going to write torque equals to I alpha only. We are going to write torque equals to I alpha only. Mg into L by 2 equals to moment of inertia into alpha. We are trying to find alpha, right? So mg into L by 2, but what is the moment of inertia? When you write the moment of inertia, you need to be really careful, guys. Because when the system is rotating, let us say the system has come down like this. It's not just the rod, the particle mass is also going in the circular motion. The particle mass is also going in the circular motion. So along with the moment of inertia of the rod, ml square by 12, you have to add the moment of inertia of the particle mass also, ml square. You write the entire moment of inertia of the system. So that is what you need to put there. ml square by 12 plus ml square alpha. You need to solve that. Of course, if you solve that, you'll get some answer. I would get the answer as 6 by 13, I guess. 6 mg by L or something like that. No, 6g by L. 6g by 13L. Yeah, the answer will be 6g by 13L. Okay, guys. So when you write a problem like this, I hope everyone get it. Like, do you want me to explain it again, or do you want me to discuss another problem similarly? I'll just discuss another similar problem. Okay, like take the same rod hinged in the middle, and I put 3m here, 2m here, and the entire rod's mass is m again. The length of the rod is L. Okay, so let me do the entire calculation. I'm going to explain the entire problem. There are different forces acting. Mg is acting here, 2mg is acting here, 3mg is acting here. So who is capable of creating torque? This is not. This cannot create any torque because it is passing through the hinge. 2mg will create a torque like this. 3mg will create a torque like this. So I'm going to write the torques as 3mg into L by 2. Since this is L by 2. 3mg into L by 2 clockwise minus 2mg into L by 2 anti-clockwise. 3mg into L by 2 minus 2mg into L by 2. That is a net torque equals to I alpha. Let me clearly write. This thing simply becomes mg into L by 2, 3mg minus 2mg. The moment of inertia, when I write the moment of inertia, I need to be careful because all the three masses, the rod is rotating, this particle is rotating, this particle is also rotating. Remember, moment of inertia is not some vector quantity. You don't need to subtract or add. All you need to do is simply add the entire moment of inertia. Whatever is rotating, you simply add it. right? The whole system is rotating, so you simply add all the moment of inertias. So when I write it, ml square by 12 for the rod plus two particle masses going in circular motion. So 3m into L square plus, let me delete this one. 2m into, oh, L by 2 square. I'm sorry, guys. I'm sorry about it. When you write the moment of inertia, ml square by 12 for the rod, 2m into L by 2 square. Similarly, 3m into L by 2 square. Okay, I'm really sorry. In the previous problem, did I take it wrong? Sorry, guys. Here the distance is L by 2. Since it is rotating and the distance is L by 2, you write the moment of inertia of this particle as m into L by 2 whole square. Yeah, Karthik, thanks for mentioning that. It's basically like, it doesn't matter. Whenever you're writing the moment of inertia, you're writing like ml square by 12 plus 2m r square plus 3m r square, where r is the distance from the center. Here r is L by 2, here r is L by 2 because both the particles are at a distance L by 2 from the center. That's all. Okay, even in this problem also, it was at a distance L by 2. So you're basically writing m L by 2 square. So m L by 2 whole square. The whole system's moment of inertia is ml square by 12 plus. So yeah, I think I got the wrong answer previously. Now you get the right answer. Okay, I'm sorry about the previous problem. Okay, guys, do you get that? Yeah. So these kind of problems you need to be careful. I'm going to give you one more. Anybody's facing any issues? I didn't get any answers from any of you. Okay, why don't I give you a problem and check whether you're getting the question or not? I mean, the way I'm doing it or not. Okay, why don't I give a problem? The same values, except I'll just, I mean, the same kind of a problem, except I'll change all the values and let's see if you can get the answer. The rod's mass is 5m, length is L, one particle mass here, 3m, another particle mass here, 6m. Okay, try to take some time. I'll give you a minute or something. Try to find the angular acceleration. Of course, the system will rotate like this since 6m is heavy. Try to find the answer. Still no answer, guys. 1 minute is over. Like you need to practice enough. When you look at the problem with enough amount of practice, you'll just directly do the problem. I mean, a lot of people do that way. They don't really find it that difficult anymore. Okay, Harshvardhan comes up with the first answer. Let's just see other people have the same answer or not. Harshavardhan. Okay, Sumantraj came up with a complete different answer. I don't know how. Harshavardhan and Mazida, you have the similar answer. I'm not sure if it's the right answer. Harshavardhan and Mazida have the same answer. Sumantraj, I don't know where you got the answer from. Okay, people are hitting me with random numbers now. Okay, most of the people are coming with the same answer as Harshavardhan and Mazida. Let me check, just check it. Okay, the values are big. There is 5 mg acting here, 6 mg acting here, and 3 mg acting here. I'm going to write the torques This time I'll take anti-clockwise as positive. It's our call. It's totally our call, which has anti-clockwise as positive and negative. So I'm going to write 6 mg into L by 2, 6 mg into L by 2 minus 3 mg into L by 2. That is a net torque equals to I into alpha. Now when I write I into alpha, that is where the tricky part is. So 3 mg into L by 2, the net here is I. Moment of inertia is 5m into L square by 12, that is for the rod, plus 3m into L by 2 whole square, that is for the particle mass 3m, plus 6m into L by 2 square into alpha. So you solve this entire thing, you find the alpha value, that is the value. I don't know. A lot of people send me saying 9G by 16. If your calculations are right, you could be right. I'm not sure about. I'm not sure whether your calculations are right or wrong, guys. Some Sumantra is asking me to solve. Okay, fine. Let me solve it. 6 mg L by 2, and on this side, let me clean this up. I'm intentionally slow. We're going very slow, guys. Okay, because a lot of people find the topic of rotational dynamics very difficult. So 12, 6, 3 is 18 ml square plus 36 ml square. Do you all get it this big? 636, yeah. If I'm going anywhere wrong, please let me know. And 3, oh, I can't cut down 3. I have 3 right there. Yeah. M goes, okay. Is there anything that I can do? 18GL equals to 5 plus 18 plus 36. How much is it? 36 plus 18 is Karthik and Aditya. What is it?
So it won't be 36 ml square, sir.
Oh, okay. I made a calculation mistake here.
4, sir.
I'm sorry. I'm sorry. I'm sorry. I'm sorry. It totally slipped off.
Yes, sir.
My mind is so lazy today. I'm not even doing proper calculations. Anyway, let me look at it. So 4, 3, so 9 ml square. 4, 3, so 18 ml square. So sum of these three things is how much?
Yes, sir. I got
32.
like 9G by 16L, sir. Sum
9
of
plus
this thing will
18,
be 32, sir.
27 plus 32, 32
32, sir.
L square alpha. So alpha equals to 18G by 32 L,
Yes, sir.
which is nothing but 9 by 16. 9G by
Yes, sir.
16, guys.
Yes, sir. Same answer.
9G by 16L. You made me do a calculation. This is probably the first time I've made a calculation entirely in a class. Basically don't do that. I just leave it for the students to do it. Anyway, so I hope you clearly get the point. Like whenever you see a body, I'm going to change the body now to another body, which is a disc. A disc is hinged in the middle. Now the disc is like in a vertical plane. Okay, it's not in a horizontal plane. The disc is like this in a vertical plane, and to a disc a particle mass is sticked. The disk's mass is 3m. Let us take the particle's mass is 2m. It is sticked. So there is a vertical disk hinged at the middle, hinged at the center. It can rotate like this. So there's a particle mass which is sticked to the end of the disk. So how do you do this problem? There's a difference. Like you clearly need to observe this thing. Uh, I'll do the problem. 3 mg, 2 mg. Anybody is giving the answer? Don't just wait for me. You also can do it. 3 mg won't create any torque, so 2 mg will create the torque. 2 mg into R is a torque equals to I alpha. Whenever I write the moment of inertia, I need to be careful that it's not just the disk that is rotating, the particle is also going. So disk's moment of inertia is 3m into R square by 2. That is the moment of inertia of the disk, mr square by 2, plus the particle mass 2m into the distance is basically r square. So if you solve this thing, you get it as, I don't know, you calculate it. I don't want to calculate it. If you didn't get it, if you don't understand what I just did there, please let me know. Okay, but you don't have to. Mazida says the answer is 4G by 7R. Yeah, the answer is right. This goes that way, 4G by 7R, right? Now, I'm taking you slowly to another, towards a specific point here, okay? The same disk hinged at the middle. One particle mass is sticked here. The disk's mass is 3m. One particle mass 2m sticked here. Another particle mass m sticked here. Do it quick and give me the answer. Who's gonna do it quicker? Obviously not me. I'm just a sleepy face today. I'm so sleepy. Who's giving the answer? Okay, Sumantra's already gave the answer. Good. But I don't think it's right. Ah, yeah, it is right. It is right. Sumantra is right. So the torque, this is rotating in this direction. This is trying to rotate it in this direction. I mean, the torques are in that direction. So I'm going to write 2mgr minus mgr. That is the net torque equals to I into alpha. How much is I? 3m into r square by 2 plus 2m into r square plus m into r square. Sumantraj is wrong. So the torque is ngr equals to by 2. The whole thing is 3, 6, 9 mr square alpha. So the torque is 2 by 9, 2g by 9r. Sai, Harshita, and Mazida already gave the answers. The alpha is 2g by 9r, guys. Now, look at this problem clearly. The disk is hinged at the middle. Now, I'm going to take a similar disk hinged at the middle only, but I'm going to hang the same two masses, 2m, m. So the mass of this thing is 3m, this thing is 2m, this thing is m. Can somebody raise your hand? Don't try to type it. Can somebody tell me what is different now? What exactly is different now? Can somebody tell me? Aditya.
So here, like these masses are way out of the disk only, sir. If I consider that pulley as a disk, these masses are like outside the disk.
Now, the important point, simply to put it, the masses are not in a rotational motion at all. The masses are simply linearly going. So if only you put these masses in the rotational motion, you're completely getting it wrong. So these two masses, m and 2m, are in a linear motion. It's just a disk which is only in rotational motion. So you have to treat them completely separate. You have to completely treat them separate. So that is what we are going to do. Now, yesterday I already gave the reason, Aditya can go on mute. Yeah. Yesterday I already gave the reason why we consider the tensions different. T1, T2. So this is T1, this is T2. So this whole string has a tension T1, this whole string has a tension T2. I already mentioned this. If only there aren't different tensions, who is going to create the torque on the disks? Who is going to rotate the disk in the first place? Since the disk is rotating, we have to mention the point that the strings clearly have different tensions. Now, this is reality, guys. Basically, this is reality. The strings always have different tensions whenever a body in the middle is involved. The strings always have different tensions. But in those problems, since we didn't have any mass for the pulley, since the pulley doesn't really have any inertia, we used to consider that the tensions are equal. But now we cannot do that. Okay. Now slowly check this thing. What's going to happen? Let us just say this system is going to accelerate like this: A downwards, A upwards. Are you ready, guys? I'm going to write all the forces in the system. 2mg, mg. Now, I'm going to write all the equations in the system. Clearly watch this thing. First, this equation, this part. Okay. 2mg minus T1 equals to 2m into A It is a basic equation everyone writes. Next thing, uh, T2 minus mg equals to m into a for this body. Since it is going upwards, I'm taking T2 minus mg equals to m into a. I hope you get this part clearly. Now, the next thing, for the disk, it is rotating like this. Since the body system is moving like this, the disk is rotating like that clearly. I'm going to write T1r minus T2r. This is the net torque, which is equals to I into alpha. Let me clearly properly write it. T1 minus T2 equals to R into R equals to 3m into R square by 2 alpha. We have three equations, guys. Clearly watch. This is the first masses equation, second masses equation. This is the disk's equation. Okay, do we clearly have it? Aditya, yeah, what's your doubt?
So you won't use that 2m and m using during the inertia of this moment.
Exactly, they are not even rotating, right? They are in linear motion now. That is the reason, that is a thing that I wanted to see. Like I want you people to clearly see in this situation, this is rotating, this is also rotating. Like you see that they're going in a circular motion. Here, they're clearly going in a straight line motion. They're not even a circular motion anymore. I want you to clearly see the difference. Whether the bodies are just in the rotational motion or just in a straight line motion. You need to clearly see that. You get that now?
So if I see any body observing a linear motion, I should not include that body in that
The
rotational
rotational
motion
motion at
formula
all
only.
anymore? No, not at all. Like even in every problem that we considered, like this problem, 2m is clearly going to like go like this. In the previous problem, 3m
At
is going to
alpha.
go like this, 6m is going to go are in the opposite direction, right? 6m and 3m are going to go like this. Or in this problem, 2m and this thing are going like this. They're attached to the system, so that is why they used to go like that. But in this problem, they're not. They're not going in that direction. They're clearly going in a straight line motion. You see that now?
Yes, sir. Now it's clear, sir.
Yes, yes. So now I'm going to solve these equations. This already looks like it's a big thing. Guys, I'm not going to write the equations again. Just try to add them, these three equations, the things which are like marked in blue. Try to add these equations completely. Like you have a plus T1, you have a minus T1. You have a plus T2, you have a minus T2. So they get cancelled each other. They get cancelled. So the only thing that you have is have here is 2mg minus mg. That's all. On the left side, you have 2mg minus. Oh, wait a second. I'm sorry. I have to cancel this r. I have to cancel that r. Now all I have in this thing is 2mg minus mg. On the other side, what do we have? All I have is only positive terms. So I'm going to add all the terms on the other side. You clearly watch 2ma plus ma plus 3mr by 2 into alpha. 3mr by 2 into alpha. I'm going to discuss more problems, don't worry, okay? So 2mg minus mg equals to 3ma plus 3mr alpha by 2. Guys, this is the important point. Remember the idea of constraint relations? We have a separate constraint relation here. We have a very important, a special constraint relation here. Everyone knows that if this is going down with A, this is going up with A. But we also know that this is going with alpha and the radius is R. So this specific point is also going with R alpha. The linear acceleration of that specific point is nothing but R alpha. Now the acceleration of this point and this point must be equal. That is according to the constraint relation. So A equals to R alpha. That is how I'm writing it. Clearly observe that. The point that we have on the string that has R alpha from the rotation, but it is connected to the block which is also going with a linear acceleration A. They have to be equal, otherwise the string breaks. That's the constraint relation. So I'm going to use A equals to R alpha. So this R alpha will be written as mg 3ma. That R alpha will be written as 3m by 2 into A. Now the problem gets really easy to solve. This is nothing but 7a by 2 equal to g. A equals to 2g by 7. Once you have A, You can write alpha also. Alpha from this thing, alpha r alpha equals to a, which is 2g by 7. So alpha equals to 2g by 7r. Okay. So can you explain the tension cancelling part again? Zaid, I'll do another problem. You'll clearly get it. Okay. I'll do another problem. You'll clearly see that. I will simply explain a similar problem completely. Okay. Okay. Everyone's going to parallelly do this with me. Everyone's going to completely parallelly do this problem with me. So get ready. I'm going to give you the masses and I want you to parallelly give me the answers. All right. I hope everyone's ready. Are you ready, people? Are you ready? Wait a second. What were the masses? Okay. Are you ready? 5m, 3m, m. Now, just like in Newton laws, I also have a shortcut to this also. So I can directly give the answer. Do you want me to write the answer immediately? I am already giving the answer. Do you want me to? Acceleration goes as 2mg by 3m plus m plus 5m by 2. So it's like 4g. Oh boy, I'm sleepy. Yeah, 4g by 13. Yeah, I'm right. So check that and let me know if you're getting the same answer or not. Anyone has any answers? I could be totally wrong also, so you better check the answers and let me know. I'm going to put all the values like the free body diagram for you, just in case. Where is that beautiful green that we used to have? Yeah. No answers yet. T1, T1, T2, T2. And I say this is accelerating downwards, this is accelerating upwards, and it is rotating with alpha. Mazida, do you get the same answer just like me? Did I give the same answer? I think I gave the same answer. Yes, Mazida, you are right. Okay, people are getting the same answer just like mine. Did you all just copy from me? Okay, now everyone's giving the answer. You all copied it from me, I know. Zaid, since you asked, watch each and everything. For this body, it is 3mg minus T1 equals to 3m into A. For the second body, T2 minus mg equals to m into A. For the pulley, I'm going to write it here. I cancel it and put the equation there. Okay, so since it is going rotating like this, T1r minus T2r equals to moment of inertia 5m into r square by 2 into alpha. R cancels. So I have T1 minus T2 equals to 5m r alpha by 2. I'm going to put it here. T1 minus T2 equals to 5m r alpha by 2. So when I try to add all these three equations, like all the terms are going to get added, right? So this plus T1 will get cancelled with minus T1. This plus T2 get cancelled with minus T2. Will be left with only these two terms, which is nothing but 2mg. On this side, this is simply A. So you have 3m plus m plus 5m by 2 into A. If you do the calculation, you will get acceleration equals to 4g by 13. and alpha accordingly. And Aditya is asking me to teach the shortcut. Of course I won't. Why will I do that? I'm a bad person. You do know that. I'm going, sir, previous problem. What happened, Mazida? Mazida, you please raise your hand and speak up. What was wrong in the previous problem? Yeah.
Sir, can you please show the last part of the previous problem, sir?
Here?
Yes, sir.
Yeah, okay.
Still above, little.
What?
Sir, calculation, sir. I have doubt.
Did I make a calculation mistake? No, I didn't make any calculation mistake here. I mean, even with the
Sir,
short,
I think 2G by 9.
you're getting 2G by 9R. 2M plus
Yes, sir.
M plus 3 by 2, right? So, oh, right, it is 9. I made a calculation mistake. Here, 2M plus M, I missed that MA. So, we have 3 plus 2, 6 plus 9A. This is 9. So, yeah, this is 9. I'm sorry. 2G by 9R. It is 2G by 9R only. Thanks for reminding me again. I do calculation mistakes all the time. So I can afford to make mistakes. I'm not the one who's attending the exam. Okay. You people shouldn't make any mistakes. I'm giving the next question. Get ready, guys. This problem is a bit different compared to the previous problem. Of course, I'm going to give the answer immediately and make you feel jealous about it. But we can't do anything about it, right? And the answer is 6G by 13, I guess. Or is it? Wait a second. Yeah, I think it is. No. Yeah. It is. I got the answer. So make a quick calculation and let me know. 6G by 13 answer is. Of course, the radius is R if you want the radius. Come on, guys, do it fast and let me know the answer. Why don't I do it parallelly with you instead of just sitting idle? 3 mg is here. This mg is not going to work because it's not going to do anything. So we don't have to worry about that mg. And tension T1, tension T1, tension T2, tension T2. And the equations go like this is going down, this is going horizontal. So 3mg minus T1 equals to 3m into A. The second equation, T2 equals to m into A. The Pulley's equation, T1 minus T2 into R equals to 5m R square by 2 alpha. You solve all these equations. Mazida just gave the same answer that I gave. She copied. So if you do that, you solve it, you'll get acceleration as a 6G by 13, guys. Okay. Harshavardhan also got the same answer. Raghav says the way I'm doing the shortcut is like I'm taking the net force, adding to the masses, including the pulley. Of course, that's what I'm doing. Like that's what I told you people. You look at the net force driving the system and look at the inertia. In the previous problems in the Newton laws, the only thing that used to have inertia is basically the masses which are accelerating. Along with that, you need to add the inertia of the, what do you say, the disk also. That's all. Okay. Aditya got the wrong answer. He says it's 5G by 11. No, Aditya, it's not. It is 6G by 13. Sorry, he says 6G by 13, but the answer is Wait a second. The answer is 60 by 13. You are saying 60 by 11. No. Answer is 60 by 13. So that is one more idea, guys. I can give more problems. Like, yeah, we have 15 more minutes or 10 more minutes. I can discuss one more problem. I'm not doing the calculation. The equations are right here, guys. All you need to do is just do some calculation. Please try to put some effort into it and do some calculation. You will get the answer. Okay. Look at this question. How do we talk about it? Yeah, there is a question like this in HC or my guess. Okay. So the moment of inertia, he directly mentions the moment of inertia. Instead of giving masses and radiuses, he directly says I1, I2 and M1, M2. Now, so to solve this problem, to find the acceleration, let's just imagine this is the heavier one, this is lighter one. Just imagine that this is a system. This is basically like you have three tensions now, T1, T1, T2, T2, T3, T3. But when I write the answer, you will clearly see how simple it is to write the value. I'm directly writing the acceleration. Watch it. M2 minus M1G by M1 plus M2 plus I1 by R square plus I2 by R square. That's the acceleration, guys. The radius must be mentioned, R1 and R2. Otherwise, you can't do it. So if it is R1 and R2, let's just put it as R1 and R2, and that's the answer. That's the acceleration. So no matter how difficult the problem looks, you can always find the acceleration of the blocks as simple as this. Okay, this is a simpler and much easier way to do it. All right, guys. Yeah. Let us discuss a new problem today. I mean, since we have time, sir, got that technique. Okay, Aditya got the technique now. So yeah, why don't you use this same technique every problem that we discussed? Like, why don't you, when you watch the topic again and you watch the class again, just go through the same formula, use the same idea, and check for all the answers. I want to discuss a new model, just a new idea here. Okay, a rod, but is hinged at the end. The rod has mass m and length L. When it is released like this, it's like the by pencil and it is hinged like here. When it's released, it is clearly accelerating horizontally, right? I mean, like it is angularly accelerating. There is some angular acceleration. Right at the beginning, it has some acceleration angularly. How much is it? So when you want to look at this problem, you need to look at all the forces acting on the system, mg, and obviously normal force is there. But we don't need this normal force. Everyone knows that. We don't need to talk about that normal force, but because that normal force is not creating any torque. That normal force is not creating any torque. So let's just simply look at this problem. Mg is going to create some angular acceleration or some torque. L, perpendicular distance is L by 2. So the torque simply is mg into L by 2 equals to I alpha. Now, I hope everyone remembers the moment of inertia of the rod about one of its end, which is ml square by 3 into alpha. So L cancels out, mm cancels out, alpha comes as 3g by 2l. 3g by 2l. Okay, so this is how you find the angular acceleration. But the problem is not over yet. Sometimes what they do is they give the same problem. They give the same problem about the same thing. Yeah, why don't I discuss it here itself? They don't ask alpha, they ask the acceleration of this. Let me just mark them with another color. Okay, the acceleration of this particle, or acceleration of this particle, or acceleration of this particle. Specific particles, they have some linear accelerations, right? So like A1, A2, A3, how do you find this acceleration? That's what they ask sometimes. So in this problem, I got a alpha value, but I want A1, or I want A2, or I want A3. What do I need to do? Since I already know the alpha value, If I multiply it with perpendicular distance, A equals to R alpha. So L by 2 alpha for this. Let us say this distance is given as L by 3L by 4, let's just say. So this value is nothing but 3L by 4 alpha. What is this value? It's basically L alpha. Since the perpendicular distance clearly is L for this particle. So they all have accelerations, like angularly they're accelerating, but the linear accelerations are this. If they don't they don't ask you the angular acceleration, they might ask you the linear acceleration also sometimes. So you need to be careful about it. Okay. I'm going to give you one problem and end the class, just the last problem. In a vertical plane, a disk of mass m and radius r is hinged here. A disk is hinged on its edge. It's like, I don't have a disk here. Well, let's just say this is the disk. It is hinged here and it is released. What is the angular acceleration? How do you solve the problem? Do a quick calculation. Don't go wrong with the moment of inertia. Just make sure you get the moment of inertia right. If you remember the values, try to get that right and you'll get the answer. Zero. Aditya says answer is 0. How stupid are you, Aditya? Why is it 0? Aditya,
How
what
will
is
it move on this, sir?
what?
It's like circle. How it will move from that point, the point where it is hinged.
What? If it is a circle, it is hinged at the edge. It will still rotate, right? Like, it's not a circle, it's a disc. I said it's a disc. It's a disc, but it's hinged at the edge. It can be hinged at the edge. Who said it cannot be?
Yeah, it can be hinged, but how will it move, sir?
Like this. Can you not see my footage? Like, am I not visible to you?
No, yeah, visible.
But what's the problem? Like, this is a disc and it is
Oh,
hinged
I was
here.
thinking, I would thought like the wall will extend downward also.
Oh, no. The wall is not extended, of course, right? So the wall is
Yeah,
like,
I thought the wall is downwards, like
yeah,
this.
yeah. No, the wall is
Going,
like,
so how will it rotate,
the
first
wall
of
is
all?
this, the wall is not coming in way. Okay. Yeah. We'll have to do some questions like this. The wall is not coming in the way. So mg, the perpendicular distance is this time r. So the torque is mg into r equals to I alpha. Harshita already gave the answer. The moment of inertia, how much is the moment of inertia here? About this point. Anyone remembers? It's like if the disk is here, you know the moment of inertia about this as mr square by 2. You have to shift it. Mr square by 2 plus mr square, 3 by 2 mr square. So 3 by 2 mr square, the moment of inertia, the new moment of inertia. So mgr, m cancels. So alpha equals to 2g by 3r. Harshita got it wrong. Maybe you got the moment of inertia wrong, Harshita. It is about it rotating about the new hinge. Moment of inertia needs to be taken about that hinge. That's what it is. Like, that is how you solve the problem. You need to take the moment of inertia about which it is rotating. So you need to take the moment of inertia, the new value. All right, Harshita, you get it? So that's it, guys. We've discussed a lot of good problems today. I think you have enough knowledge about the problems that you're going to solve now. Obviously, like I already asked you to complete this page. I hope this page is completed. And this page, look at all the questions: 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 30. 37 is a bit difficult. 37 is a bit of a difficult problem. I will discuss that. Okay. I mean, taking the constraint relations and all, it is a bit difficult. 38, 39, 40, and all these things can be solved again. I mean, it gets a little difficult onto this side when you come to 42, 43, 44, 45. They're basically equilibrium problems only, but it gets a bit difficult to solve the problem. So yeah, you can happily go up to 45 as long as you're comfortable. After that, the problems are from the next week syllabus. So I may discuss them tomorrow, or tomorrow we can just take it as a doubt session, and we can continue the class on the Saturday. So before I end the class, just about the class, if you have any doubts, please let me know. Just about the class, if you have any doubts, let me know. Otherwise I'll just show this animation. I've already prepared it for you and I didn't show it to you. So what we have here is two pulley systems, where in one system the mass is not like the pulley has no mass. In the other system the pulley has mass. See how they move. Where the pulley has inertia, it is not moving that fast. Because of that pulley's inertia, it is moving really slow. You see that? So pulley's inertia definitely comes into an act. All those values, you don't have to worry about them. Okay. So I just have this animation. I just wanted to show it to you. So guys, that's it. No doubts, I guess. Nobody raised their hand. So if you have any doubts, just ping me and we will talk about it. All right. Thanks so much and bye bye.